do you think I was going to say? Like go out in the quad and hold hands or something? Right. I mean, I like you all, but we're here for a purpose, right? Okay, so we're going to see one more application of the right-hand rule. We've seen two applications, and really it's just one application that we've seen of a charge moving through a magnetic field. That when a charge moves through a magnetic field, it feels a force. And we use that force to generate electricity. We move wires through magnetic fields, and that causes the electrons to move through those wires, and that's what allows us to, have electricity. We also get a magnetic field when a charge moves through a wire, because you remember the basic thing that causes a magnetic field is a moving charge. We said at the very beginning that permanent magnets, they have a magnetic field because they got these electrons that are moving back and forth, and they generate a magnetic field. So a moving electron causes a magnetic field. So in a similar way, a current in a wire creates a magnetic field that surrounds the wire. To find the direction of this magnetic field, we'll use the right-hand rule. We let the thumb of your right hand go in the direction of the current. Then your fingers wrap around to give the direction of the magnetic field. It's a circularly symmetric field, so our fingers wrap around to give it. And it looks like this. If I have a current that's going in this direction, like this, then I let my thumb go in the direction of the current, and my fingers wrap around. And so on this, the magnetic field, well, like it's drawn here, will go around like that. Now we can represent this in a number of different ways. Like for example, I have this wire, and the current is going upwards. What is the direction of the magnetic field on the various sides of this wire? Well, what about on this side? Is it into the page or out of the page, left or right? Into the page, right. Thumb in this direction, fingers go into the page. And what about on the opposite side? Out of the page, right. So I would have a magnetic field that would be into the page on this side, and then out of the page on this side. I would have this magnetic field going all the way around my wire. Now, if I were to come on this side of the wire, it would be to the right. The magnetic field would be pointing in this direction. And then if I were to go on the back side of the wire, it would be pointing to the left. So like if this is my wire, my magnetic field is going to go like this. It's going to circle around it. Now, the magnitude of that, let me show you another way we can do that. I can also say that, well, this is my wire. This represents the current. And so like if this is my wire, the wire goes into the page and the current is going in that direction. In that case, the magnetic field, thumb in the direction of the current, is going to fold around. Is going to be clockwise or counterclockwise, the magnetic field? It's going to be clockwise. Right, so in this case, the magnetic field, which I'll do in blue, is going to look like this. And it actually extends out, and we could draw field lines that go out to, infinity basically. It goes to zero eventually, but it extends outward. So I have this magnetic field surrounding this wire that goes into the page. All right, the magnitude of this magnetic field, this is given on your equation sheet, but it's proportional to both the current and the distance from the wire. If the current increases, the magnetic field increases. You got more charges that are moving, more magnetic field. What happens to the magnetic field as you move further away from it? Does it increase or decrease? It decreases, right. So B is equal to mu naught times I over 2 pi r. This is the magnitude of the magnetic field. Here mu naught is the permeability of free space. This is related to K. If you remember Coulomb's constant, they're related. We're not going to get into what the physical meaning of it is. We'll just sort of take it as a constant for now. That the magnetic field is proportional to this permeability of free space. And you don't need to know this word, like what it means, but you just need to know what the number is, and it's on your equation. Okay, know how to calculate what is the magnetic field at a certain distance. Brittany? Yeah. For which one? This one right here? This one? Okay, so my current is going up. So I actually have, where's my pencil? If I think about this being my wire right here, I'll let my thumb go in the direction of the current, and then my fingers wrap around like this. So on this side, it goes into the page, but then as I go around on the other side, it comes out of the page. Now in the front, it goes in that direction. In the back, it goes in that direction. So let me rotate this towards you. It will actually now go like this. It depends how you're orienting it, but the magnetic field will always go like this. Always surround that wire. Does that help a little bit? I like this chapter, not because, you're probably never going to use the right-hand rule again, but I like it because it allows you to think about things in 3 dimensions. And some of you just don't have much experience with that. But it's important to be able to do so for other fields, like, organic chemistry, right? You guys think about 3 dimensions a lot in that class? Yeah, because you have these molecules that are oriented in different ways. So it's useful to be able to think in 3 dimensions. All right, let's try this. What is just asking the direction here, what is the direction of the magnetic field of these 2 wires? You have 2 wires that are both contributing to a magnetic field, at the point A. What is the direction of it? Is it into the page, out of the page, to the left, right, or maybe there's no magnetic field at all? If you finish this one, go on to the next one. All right, let's stop at 110, just 5 more seconds. A couple more seconds. Okay, I think that's right. Let's take a look. So I let my sound go in this direction. It comes out of the page, so it's out of the page due to this wire. And on this side, it's also out of the page. So for the wire on the left, I have a magnetic field that's into the page, out of the page, out of the page. For the wire on the right, I have into the page on this side, out of the page on this side. And so in the middle, I get both both out of the page. They're both coming towards you. So I get these 2 vectors that are going to add up. What would happen if this current was going the opposite direction? What would be the magnetic field? There'd be none, because it's a vector quantity. And if I get 2 magnetic fields, one of which is opposite the other, then it cancels out. All right? Did I ever tell y'all that I'd had like this once? I did this theatrical performance all about puns. Ever tell you that? It was a play on words. Good job. Let's try this next one. All right, which of these has the largest magnetic field at point P? These get a little arduous. If I give you one like this on the test, I'll try not to give you 12 wires that you have to do. I'll give you a few. But which of these gives you the largest magnetic field at point P? Let me just sort of get you a little kickstart here. If I think about this first wire, right here, it's out of the page, then I know that the magnetic field is like that. That means at point P, my magnetic field is going to be in that direction. Isn't that right? Yeah, it wraps around. And so at point P, the vector due to this wire is going to be up and in this direction. is you take the vector that's tangent to the circular path. So at that point, due to that wire, the magnetic field is in that direction. And in fact, when you get good at this, I'll go ahead and draw the rest of these for you. You can compare your answers. If that one's the red one, if this is the green one, it's going to be in this direction. And if this one's the purple, it'll be in that direction. So that first configuration of wires will give you zero magnetic field at the middle because they all cancel out. So the answer is not A. It's the point of it. But you take the same process for the other three. Okay? It's related, yeah. So in lab, you had this coil of wire that generated a magnetic field, and when you turned on the magnetic field, it added up with the Earth's magnetic field to cause the compass to move one way or the other. So yeah, it's similar that we are adding two magnetic fields. They're vectors, so you can add them up just fine. I said A is not the right answer because it has R. It could be D, but it's not A because A has zero magnetic field. All right, let's stop in about 10 seconds. Let's go to 2:30. So if you have one of these on the test, and you will have wires on the test where you have to find the magnetic field, I won't give you one this long. This one takes a while to work through. All right, 2:33. Okay, I think B is right. Let's take a look. So if I'm looking at this one first, it's in that direction. This one, it's in that direction. Due to this one, it's in that direction. And then due to this one, it's in that direction. So that gives us a net magnetic field that points down. They're vector quantities. I'll just add them up. I'll step through it one more time. So the purple one here is into the page, goes into the page, and so my magnetic field goes around like that. So at this point, it's down and to the left. The green one is out of the page, and so it folds around and gives us that vector. The blue is out of the page, right there, and then the red is into the page, so it folds around and gives us this vector. I think on this one you get 0, is that right? Yeah, so on this one you get 4 vectors that are all equal but opposite. And I'll leave you on your own to try that out. There are some homework problems to help you with this, but look back at the old test, and we'll do some old test questions this morning for practice on this, because you'll certainly see stuff like this on the test coming up. I think it's in a couple of weeks, am I right? Test? Is it 2 weeks from today? The 30th? 31st? That's exciting. I hate tests. Don't y'all hate tests? Hey, I took a test this morning, and my last test I made like a 75 on. I'm like, oh, that's not right. But I did. I made a 75. And so I completely changed the way that I studied. Like I made note cards, and I quizzed myself a lot, and I made these little podcasts of me like teaching the material to myself. And then I gave the podcast to my whole class, and they were all like, gosh, you're the greatest. But this morning, what did I make on my test? 100%. I missed a couple, but I got the bonus. No, it's okay, you can say it. Yeah, you're awesome, or good job, or just, yeah, aghast, speechless. What? Okay, let's, I'm done. So, we can get a magnetic force then between two parallel conductors. And we'll use this, you can use this to cause two magnetic fields to sort of interact, where you can have forces between two different wires. It's nothing new, but let's sort of step through how this works. So a current carrying wire creates a magnetic field. And we also said that when you have another wire that's also carrying a current, it experiences a force due to this magnetic field. So imagine this. I have these two wires. This wire creates a magnetic field in which this wire sits. So this wire is going to experience a force due to this wire. This wire is current in this direction, so the magnetic field is into the page, out of the page. So if I draw the magnetic field for this wire, it's into the page, out of the page, and that extends out over to this wire. And now if I think about the force on this wire, I have I in this direction. I have my magnetic field is out of the page. Go back to our first iteration of the right-hand rule. B is out of the page. This. And so that tells me that the force on this wire is acting down. Now there's actually a force acting on this wire that is down because of the magnetic field that's generated by this wire. Let me step you back through it. This wire creates a magnetic field. This wire, which has a current in it, sits inside that magnetic field, and so it experiences a force. That's that ILB sine theta business that we did before. This force then attracts this wire down to this wire. Now, we can leap. I mean, you can go through the same procedure for the other. That is that this wire creates a magnetic field that is into the page, like that, out of the page on this side, and then the bottom wire, which has a current now in this magnetic field, will also experience a force up. But we could leap to that just from Newton's third law, because I know that if I have a force here, then I'm going to have a force that's equal and opposite. Because if I have one force, I have to have an equal and opposite force, and this is that reaction force that we saw in Newton's third law. And we can calculate that. This is on your equation sheet, but F12 is equal to I1 times L times B2. Now what this is the current in the first wire. This is the magnetic field created by the second wire. You follow me? I have one wire that's making a magnetic field, and then the other wire responds to it because it has a current in that magnetic field. So it's equal to ILB2, and then putting together what we've already found, I know that B2 is equal to mu naught I2 over 2 pi r. We just saw that. That's the magnetic field due to a long straight wire. And so I can put those two together, and I get this is equal to mu naught I1 I2 L over 2 pi r. I think that in your equation sheet, let me go away for just a second. I'll come back to this. I'll give you all a second. Don't worry about memorizing the equation. You have it, of course. Can I go? I want to show you, because it's listed a little bit differently on the equation sheet, I think. I list it as a force per unit length. Yeah, there it is. So notice here, this is that same one. Well, that's not let me do it. But right here, this is that equation. It looks a little different because it's given as force per unit length. Usually when you have wires like this that are interacting with one another, you don't really worry about the force. You want to know the force per unit length. And so just be aware of that. I think in the homework there's a problem that asks you the force per unit length. But I could certainly ask you that on the test to calculate. I have two wires with I1 and I2 that are separated by this distance. This is D, just the distance between the wires. And then this would give the force per unit length. Yeah, D here and R are the same thing. It's the separation between the wires. All right. So if you want, well, I used R because we had used R up here. Just sort of keep in your mind that R in this case is equivalent to D. It's the separation between the wires. Okay? And then as I said before, because of Newton's third law, F21 is equal just to the negative of F12. Alright, so what if your wires, these wires were in the same direction, the current? What if you flip them around? You flip one wire around the other direction. What's going to happen? Are they going to feel an attractive or an repulsive force? They're going to feel a repulsive force. That if I have one wire in this direction and the other in this direction, they will feel forces that are repulsive. For the same reason. And you can go through that procedure where you figure out what does the magnetic field do to this wire, and now what force does this wire experience due to this wire, the magnetic field created by that. In fact, this force is how we define the ampere. I don't know if you were wondering, how do you define what an amp is? I mean, we say that it's a coulomb per second, but this is really the way that we define it. And we say that if you have two long parallel wires, and they're 1 meter apart, and they carry the same current, and they experience this force per unit length, then we say that that current is 1 amp. That's the standard for 1 amp, or that's how we define the unit for current of the ampere. So these are important because these forces, well, they come up in some things, and we'll look at one application of this, but they come up here because we define the ampere based on that. Okay, just one more thing, and then we'll look at solenoids, then we'll move on to light. And then, well, never mind. Okay, so this is the magnetic field of a current loop. This is very similar. In fact, it's the same as what you did in lab, but very similar to a long straight wire. I have a loop of wire that moves around, and I have a current that flows through that. There is a magnetic field due to that. There is a magnetic field due to that coil of wire, and it's given by this. This is the magnetic field at the center of this coil of wire. All right. If there are multiple turns of wire, then you would just multiply that times n. So you'll remember in lab you did 5 turns of wire, you did 10 turns of wire, you did 15 turns of wire, and when you use the same current for the 10 or 15, you would get more deflection. That's because when you increase the number of turns of wire, then you get more of a magnetic field. That's generally true as we've been dealing with magnetic fields, that if I increase the number of turns of wire, it's going to increase the magnetic field or the force or whatever. And the big use of this is for a solenoid. Y'all all used solenoids. They're very useful to make a mechanical switch operate from a distance. Where have you seen a solenoid, or where have you heard of a solenoid? Anybody? On a car, right. So your starter motor has a solenoid, because if you think about it, you know, you have this starter down there, down inside your engine, and you need to engage it in some way to make it start. But, you know, how do you do that? And so what you have is when you turn your key, that engages an electrical circuit, which engages a solenoid switch, which takes a little bar and moves it into position to start your starter motor. So you're not directly starting your starter motor. In fact, when you turn your switch, you're actually starting a solenoid switch, sending current to your solenoid switch, which then engages your starter motor to start your car. I have a similar example in this video I'll show you. But in short, though, I have this coil of wire. When I put a current through it, it generates a magnetic field. I have a magnetic field going through it. This magnetic field up here that I drew, we can use our right-hand rule. I have my finger going the direction of the current, and it folds in and folds around. So in this case, the magnetic field is into the page on this side and is out of the page on this side, on the outside. If the current was going the opposite direction, it would be flipped. Let's look at this solenoid switch. They describe the solenoid. It's this really cool British guy. And how it interacts with the device. That you create this magnetic field when you have a coil of wire. Let's wrap up the rest of the clicker questions. I don't know where we left off. Can somebody tell me? Do you know, Caitlin? Five, 6A. What's that? We did this one last. Okay, so let's try this. Alright, what's the direction of the force on this wire? In every book I think it shows up better, but here the magnetic field is up and the current is to the right. All right. I'm going to stop at 58. 58. Okay, good. E is right. It's out of the page. I let my thumb go in the direction of the current. Or excuse me, I'm sorry. No. I let my fingers go in the direction of the current. They fold up towards the magnetic field. And so my thumb is out of the page. And that's the direction of the force, out of the page. Try this one. Feel free to ask your neighbor what they put, okay? All right, we'll stop at 50. Stop at 50. I remember our force is ILB sine theta. Here, I and B are in the same direction, and the sign of 0 is 0. So if you want to think about that, that's fine. Many of you got it, but if I and the magnetic field are in the same direction, there's no magnetic force at all. Or if they're in opposite directions, there's no magnetic force at all. Went to get blood the other day. They told me that I had type A blood. I don't have type A blood. It's typo. What's the direction of the net force on this loop? Looking for the net force. The net force. Can you see it okay in there? Up there or down there? Really? Yeah. Oh, I'm sorry. I'll try to change it, make it a little better. Alright, I'm going to stop at 1 minute, y'all. 1 minute. I'll go to 105. 105. Okay, good. C is right. Net force I can think about what are the directions of the forces, but I know the force on this one is going to be opposite the force on this one. And then the same is for these two because the currents are in opposite directions. And so the net force is going to be 0. Now, really what we're concerned about is the net torque. And that's what the next one is about. I have this coil of wire. It sits inside of a magnetic field. And I want to know what is the net torque, or rather what direction will the loop travel. My coil here has current going in that direction, and it sits in a magnetic field where the north pole is there and the south pole is there. Oh, and it rotates about an axis along there. We've had a similar question before. All right, let's stop at 110. 110. What's your 110. Okay, good. C is right. It's going to rotate clockwise. I can just take one of these. I know my magnetic field goes from north to south. Let's take the one on the right. It's going to have a downward force, so it's going to rotate in this direction. This one will have an upward force. Right? Thing in the direction of I is out of the page. Magnetic field is to the right, like that. And so the one on the left has an upward force. This one has a downward force. The force is up over here. Force is down over there, clockwise. Now remember, it only does a half turn. That it'll go, and then the directions of the current flips on both sides. So it's going to go, and then it'll sort of flip-flop back and forth. We want to know the magnetic field at point C. This is sort of like one we've done before, and probably more like what you'll see on the exam. You want to figure out the magnetic field due to both of these wires at point P, and then pick the correct answer. All right, let's do 110. 110. 5 more seconds. I'll see is right. Doing this first one, I know the magnetic field goes around in this direction, so at that point it looks like that. For this other one right here, the magnetic field goes in this direction, so at this point it's right there, and so they add up to give us that vector. But notice that you could have any one of these combinations. It depends how your wires are oriented. I was thinking at the end of the semester that we might take a field trip. Like they have that old Coca-Cola plant downtown, or in Thibodeau. And I thought we'd go look at some of their equipment and just sort of look at the electrical system and stuff. But afterwards, you know what? Pop quiz. Like y'all thought that was a real thing, didn't you? some of you did. I know that you did. I'm going to skip this one. It's a lot like the one we did before. But the answer is B. I'm going to skip this one too. These two, which direction will the wires experience a force? Will it be an attractive force, or repulsive force, or maybe no force at all? The current on both of these are going up. All right, let's stop at 105. Just a few more seconds. 105. Okay, good. We went through this exercise earlier, but this wire generates a magnetic field that is into the page, out of the page, and now this blue wire experiences a force that is due to that magnetic field that's towards that other wire. So these are, and there's a picture. So here they both generate magnetic fields which cause the two wires to attract to one another. And what is the direction of the magnetic field in this square loop? We did this for a round loop, but it's true for square loops or whatever kind of loop you want to do. It's still going to be true. All right, let's just do a few more seconds. We'll stop at, say, 40. We are going to go into the next chapter. Just a little bit of warning. We have 10 minutes left. Then we're going to go out the groans. That's okay. All right, stopping at 46. Okay, good. E is right. I can do my right hand rule again. Thumb in the direction of the current, into the page, out of the page. So this device has that's not right. Out of the page, or into the page over here. And out of the page, in the middle. All right. I think that's the last one. Yeah. All right, let's look at light. So next test, let's see. Did we get multi-loop circuits? No, we did, but we didn't get household circuits. So next test, we'll have household circuits, RC circuits, and then probably we'll get this next chapter and the next chapter. So as we look forward, we'll get the reflection and refraction chapter, which is next, and then probably just part of chapter 7. We'll see when we get there, okay? I'll keep you guys updated. This next chapter is short. There's more practice for you to do the right-hand rule in the homework. I would go back and look at that. Calculating torques, calculating forces. Go back and look at the homework. I go through that sometimes, or often I go through and look at those for test questions. And then also don't forget to go through your OpenStat for your OpenNet. I did send out a message about one of your OpenStat questions. Or an incorrect answer. Let's do tonight, am I right? Yeah. Were there any burning questions about it? Okay. I'll be around. So if you have any questions, shoot me an email. take a screenshot or whatever and send it to me, or drop by. I know I have class this afternoon from 2 to 3. All right. I think that the remainder of the class, like I think chapters 1 through 5 are sort of the harder chapters that we deal with in this class. So I think that chapters 6, 7, and 8 and 9, 6, 7, 8, and 9 are sort of easier chapters. We'll get into sound, which is sort of different. But I think these are not easy, but easier chapters. So if you've been struggling so far, then don't slack off for sure. But just know that I think these chapters are a little bit easier. All right, so let's look at the history and nature of light. It's actually fairly interesting. Newton thought that light was a particle. And, Newton was a pretty smart guy. Like in the millennium, he might be the smartest guy that's lived. But he put forth this idea that light is a particle. And he treated light like a stream of particles. And the reason he thought this is because he knew that light reflected. It followed what we call the law of reflection, which we'll see later. But it reflected, and that is to say that the incident angle was equal to the reflected angle. So like if I have a light ray and I shine it onto a reflective surface, it's going to bounce off of that in the same way that it was incident. So like I have a mirror here, it's a laser. If I shine this onto the mirror, it's pretty easy for me to measure the angle over which this light, is reflected, because I know the angle that it's coming in, and then I know the angle it's coming out. It's easy for me to do that, and I can find that theta I is equal to theta R. The incident angle is equal to the reflected angle. And in fact, just sort of to be correct right at the beginning, let me show you that we measure these angles. This is theta I, and this is theta R. We measure them from the normal line. And I'll show you that again later. And so that's why he thought that, because he saw that light reflected in that way. And particles, if you take a tennis ball, for example, and you throw it onto the ground, it's going to reflect in exactly the same way, where theta I will equal to theta R. Try it out. Or, like if you play pool and you bounce a ball off the, the bumper? The side of the pool table. Anyway, you bounce it off the side of the pool table, it's going to do this too. And so Newton, he was a pretty big billiards player. I guess, probably not. I'm not even sure if they had that then. But anyway, he knew that particles did this. Huygens, on the other huygens, he was a contemporary of Newton, and they all sort of hung out together, right? They were all part of the Royal Society. And Huygens thought that instead of light being a particle, he said that light's a wave. And he treated light like a wave. You know a lot about waves back then. They'd done a lot of studies with sound and other type of harmonic motion, which we'll get into in chapter 9. But the reason that he did this, or the reason that he thought that light was a wave, was because of refraction. And refraction is this phenomena that when a wave passes from one medium to another, like a light ray, for example, it will bend in one direction or the other. And we see this like with water waves. If you watch closely when you go out, you can see that the waves will actually bend when they go into different media in the water. And what I mean by that is like when the depth of the water changes or the temperature of the water changes, you'll see the waves actually bend in one direction or the other. You ever noticed that before? Like when you have water moving from deep parts of the water to shallower parts of the water, sometimes those waves will actually bend. And it's because of this phenomenon called refraction. the waves actually change speed. And we'll get into this, but we can imagine that if I change speed, I'm going to move because I have one side of my wave over here that's traveling faster than the other side of the wave over here. Some of you in lab have already done this. You did the reflection and refraction experiment. So we talked about that with a little class. Yeah. Many of you have not. I think y'all just started. So Huygens, Newton was sort of the rock star of the day, and so Huygens' idea wasn't accepted because a couple of reasons that were actually physical reasons. But waves need a medium. To travel. Like we know, and they knew at the time, that if we sucked all the air out of this room, what would happen? I mean, we'd all die. But if you sucked all the air out of this room, if I tried to talk to you, there would be no sound, because you have to have air. It actually transfers the energy from the sound wave. But they didn't know at the time that they said, well, if light's a wave, how does light get to us from the sun? Because we're fairly certain that there's no matter between us and the sun. Or how does light get to us from these stars that are really far away, that seem far away? And so that was a problem that they didn't really know how to deal with. Now we know actually that light is an electromagnetic wave, that it's an altering of the electric fields and an altering of the magnetic fields at the same time. And those things don't need mediums to travel through space. Also, they knew that waves could bend around obstacles. You ever thought of this? I mean, that's kind of cool that waves can bend around things. Like what? Can you see me? Can you hear me? Like, you can't see me. Well, y'all can see me, but you can't. Can you hear me? It's because, I mean, the speakers, but it's because the wave actually comes up and then it bends around and then it goes out into the room. And they said, we've never seen light do that before. We don't think light can do that. So they said waves can bend around obstacles, but they said light can't bend. Although we now know that light can bend, and we'll get into that in chapter 8 when we look at diffraction and interference. Okay, so this is not a true statement. Light can, in fact, bend. And he sort of showed that with refraction, but that's a little bit different. I mean, the path of the light changes, but it has to do with the speed changing. All right, so these were the reasons that Huygens' idea wasn't accepted. So for a long, long time, people said, oh, light's not a wave, it's a particle. In the 19th century, Thomas Young, he was my great-great-uncle. Great-great-great-uncle. No, I don't know. I think he was in England, so not related. Anyway, he discovered interference in light. And we'll have a whole chapter on interference. It's pretty cool, actually. And this is exclusively a wave phenomenon. And so, like, if they would have had the Nobel Prize back then, he would have won it, because it was a big deal. He showed incontrovertibly that light was a wave and not a particle anymore, because he showed that if you take two light waves, you can make them cancel out. So, for example, like if I combine these two waves, where the peak is lined up with the trough, it's going to line up to give me nothing. Or if I line up two waves like this, where the peak is lined up with the peak, and I add them together, it's going to give me a wave with a bigger amplitude. And we'll get into that in chapter 9. We'll look at interference and chapter 8, actually. So he said light was a wave because of interference. So on these, you need to know who said what. Newton, particle, reflection. Huygens, wave, refraction. And then there were a couple issues with that. Young said light was a wave because of interference. And then Einstein explained the photoelectric effect. And this is actually what he won the Nobel Prize for, not his... not that business. He won it for this, the photoelectric effect. He said that when you shine a light on a metal surface, it ejects electrons. And he said that's not really possible with a wave theory of light, so he invoked a particle theory of light. Because when you shine light on a piece of metal, you have to have a certain corpuscle or a certain quantity of energy to liberate those electrons. I know we're all right. We'll run out of time. We'll come back to this quick test next time, but I'll sort of summarize those when we come back. Y'all have a great weekend.